All right, project one for material science. Take one of one by me, Christopher, Dylan, and Noah. So we have a standard graph here of a stress and strain curve. There we go. On your y-axis, you have stress. On your x-axis, you have strain. This linear portion is the elastic region. This is your plastic region. In your elastic region is where you get Young's modulus. In your plastic region, right before it, you see your yield strength. In it, you see your hardening, your necking, and finally, the fracture or breaking point. Modulus of elasticity, as I said, is from the linear portion of that graph, as we saw. You take that, you find the slope for it, or the rise over run, or in this case, it would be change in stress over change in strain, sigma over epsilon.
So yield point and yield strength. So the yield point is the point at which material transitions from elastic to plastic deformation. And the yield strength is the stress a material can withstand without taking permanent damage. So on this graph, we found EP 0.002 or 2%. And we drew a parallel line to the right to the strain, and the point where the line intersects the stress strain curve is the yield point. And then ultimate tensile strength. Ultimate tensile strength is the max amount of force.
You're gonna keep going.
Max amount of force an object can withstand before it begins to break. The UTS is maximum between the strain hardening and the strain necking regions. The ultimate tensile strength equation is the maximum force shown below before being divided by the original cross-sectional area of the object.
Okay. Ductility. Your ductility is a material's ability to deform plastically before breaking and is measured in the percentage elongation or in your percentage of reduced area. As you can see over here, this is the before and after, the original area of the cross section versus after when it is stretching, the original length, the final length. You get it from these equations right here. For percent elongation, you have final length minus initial length over the original length times 100, because that's how you get your percent. For the percent of reduced area, you have the original area, because the original area is the bigger one, as you can see from here, minus the final one divided by the original area times 100 for the percent again. Resilience. To find the resilience of a material, you calculate the area under the stress strain curve up to the elastic limit. So during that linear region is what that means. You get that from this equation right here, which is sigma y squared over 2e. And our sigma is the yield strength. Our UR is the modulus of resilience, which is what we're here to calculate. And our E is the modulus of elasticity. You can see it here on the graph, exactly what I'm talking about, the area under this curve right here, the linear portion. Toughness. Toughness is a unit of tensile toughness, can be easily calculated by using area under the whole curve. So the entire thing up until it breaks, which you can see right here, is where you want to be. The way to calculate that, UT is the area under the curve of stress, and strain, which you can find from Hooke's law. And yeah. So to recap, I'm just going to recap quick. Linear portions for elastic, plastic, and then toughness is under this whole thing. That just went away. Okay. So our copper graph here, as you can see from the data points, this is the linear region. This is where you have your hardening and necking, and then eventually fracture point. Same thing for zinc. Linear region, necking, fracture point. And finally our alloy, copper zinc, aka brass. Same thing. Action.
All right, so here we have the graph for copper, and also we are finding the change in length and change in width, which is the change in diameter. First, we have to find the stress that is being applied to it. We are given that is a force of 4,000 newtons over the cross-sectional area, which the stress for both copper and zinc comes out to be about 1.27 kilopascals. And the given length and diameter of both of these objects is a length of 1 meter, diameter of 0.2 meters. Now, first thing we'll have to do, we'll have to use the Young's modulus for copper, which is 130 gigapascals. Once we find that, we have to find the longitudinal strain. So once we find the longitudinal strain, we take the stress divided by the Young's modulus, and for copper, the longitudinal strain is 9.79 times 10 to the negative 9th. And with that, we can find the change in length, which is 9.79 times 10 to the negative 7th times 1 meter, which is just that, 9.79 times 10 to the negative 7 meters. That's change in length. And once we use that, we can find the change in diameter. But first we have to use Poisson's ratio. Poisson's ratio of copper is 0.34. Once we find that, we take the latitudinal strain, which is negative Poisson's ratio times the longitudinal strain. So we have that, and the latitudinal strain is negative 3.33 times 10 to the negative 7th. With that, we can find the change in diameter, which is latitudinal strain times 0.2 meters, which is the diameter of the object, and change in diameter becomes negative 6.66 times 10 to the negative 8 meters. Then we're on to zinc. Here's the graph for zinc that we have, and then all the calculations. Same thing. Young's modulus for zinc is 75 megapascals, sorry. Do the same thing over again. The longitudinal strain is 1.6 times 10 to the negative 3. Same thing, we find the change in length. We take the longitudinal strain times the original length, so it's just 1.6 times 10 to the negative 3 meters. And then we have to find the Poisson's ratio again, which is 0.245. Then we have to find the latitudinal strain, and that ends up being negative 3.2 times 10 to the negative 4. Once we find that, we can find the change in diameter here, which that ends up being negative 7.8 times 10 to the negative 5 meters, so it doesn't really change at all when you add the 4,000 Newton tensile force.